Welcome to online lecture series on Fourier transforms. This is lecture number 13. In this lecture, we'll solve some problems on Fourier transforms using convolution theorem. Problem number 1 is verify convolution theorem for the functions f of x is equal to g of x is equal to e power minus x square. So we take f of x is equal to g of x is equal to e power minus x square. And we recall from lecture number 3 that Fourier transform of e power minus ax square is equal to root pi by a times e power minus s square by 4a. This already we solved in lecture number 3. You can refer to that lecture. So by taking a is equals to 1 in this equation, we get Fourier transform of e power minus x square is equals to root pi into e power minus s square by 4. So Fourier transform of f of x here, because f of x is equals to e power minus x square. Therefore Fourier transform of e power minus x square is given by root pi into e power minus s square by 4. So let us keep this equation aside. We'll use it whenever necessary. Now let us write the statement of convolution theorem, because we are asked in this problem to verify convolution theorem. What does convolution theorem state? Fourier transform of f of x star g of x is equal to Fourier transform of f of x into Fourier transform of g of x, where star denotes the convolution product of the functions f of x and g of x. So to verify this theorem, we need to prove that the left hand side, the value of the left hand side term and the value of the right hand side term are same. That is verification of a theorem. So first we consider the LHS, that is left hand side term, which is f of x star g of x. That is Fourier transform of f of x star g of x. We know that f of x star g of x, that is the convolution of f of x and g of x, is given by integral minus infinity to infinity f of u into g of x minus u du. So we have here Fourier transform of this function. We know that Fourier transform is integral minus infinity to infinity. The function, that is integral minus infinity to infinity f of u into g of x minus u du into e power isx dx. Now we will substitute f of u and g of u. We know that f of x is e power minus x square. Therefore f of u is here e power minus u square, and g of x is also e power minus x square. Therefore g of x minus u is e power x minus u whole square. That is equal to. So in this integral, we will interchange the order of we'll change the order of integration, because the limits are constant from minus infinity to infinity in both the integrals. Changing order of integration is simple. So just replacing the position of the integrals. So we get, upon changing the order of integration, we get integral minus infinity to infinity e power minus u square into integral minus infinity to infinity e power x minus u whole square into e power isx dx du. Now the integral with respect to x became inner integral and integral with respect to u became outer integral after changing the order of integration. Now, so this is what the equation we obtained. f of x star g of x is equal to integral minus infinity to infinity e power minus u square into integral minus infinity to infinity e power minus of x minus u whole square into e power isx dx du. Now in the inner integral, now to evaluate this inner integral, we substitute x minus u is equal to t. And upon differentiating both sides, we get dx is equal to dt. Now substituting in the integral, in the inner integral, we get integral minus infinity to infinity e power minus u square into integral minus infinity to infinity e power minus, in place of x minus u, we write t here, so t square, into e power is into, in place of x in this integral, we write t plus u, and dx is dt du. That is equal to integral minus infinity to infinity e power minus u square into this e power is into t plus u can be written as e power ist into e power isu, because the integration is with respect to t. We have taken outside this term e power isu. So we obtain integral minus infinity to infinity e power minus u square into e power isu into integral minus infinity to infinity e power minus t square into e power ist dt du. Now if you look at this integral here, integral minus infinity to infinity e power minus t square into e power ist dt is nothing but Fourier transform of e power minus x square. And Fourier transform of e power minus x square, as we have seen in the previous slide, is root pi into e power minus s square by 4. Therefore, f of x star g of x is now equals to root pi into e power minus s square by 4, and the remaining integral is integral minus infinity to infinity e power minus u square into e power isx du. If we consider this integral, this is nothing but Fourier transform of e power minus x square or e power minus u square, which is again equal to root pi into e power minus s square by 4. Now root pi into root pi becomes pi into e power minus s square by 4 into e power minus s square by 4 is e power minus s square by 4 minus s square by 4. That gives e power minus 2s square by 4, that is e power minus s square by 2. Therefore, the left hand side value is pi times e power minus s square by 2. So, to verify the theorem, we need to show that the right hand side value is also pi times e power minus s square by 2. For that, we now consider the right hand side term, that is Fourier transform of f of x into Fourier transform of g of x. F of x is e power minus x square, g of x is also e power minus x square. So this is Fourier transform of e power minus x square into Fourier transform of e power minus x square, which is equals to root pi into e power minus s square by 4 into root pi into e power minus s square by 4. Root pi into root pi is pi. E power minus s square by 4 into e power minus s square by 4 is e power minus s square by 2. Therefore, right hand side is also pi times e power minus s square by 2. Thus, left hand side is equal to right hand side. Hence, the convolution theorem is verified for given functions. Let us move to next problem. Use convolution theorem to find the inverse Fourier transform of I by 1 plus s square whole square. We are given that 2 by 1 plus s square is the Fourier transform of e power minus mod x. Of course, we can derive that Fourier transform of e power minus mod x is 2 by 1 plus s square. We have already seen that in previous lectures. So, now we are given that Fourier transform of e power minus x, e power minus mod x is 2 by 1 plus s square. This is given to us. Now, let us write the statement of convolution theorem for inverse Fourier transforms, which is given by f inverse of f of x into f of g of x is equal to f of x star g of x, where star is the convolution product. Now, let us consider f inverse of I by 1 plus I square, 1 by 1 plus s square whole square, because in the question we are asked to find the inverse Fourier transform of I by 1 plus s square whole square. As the linear property holds for inverse Fourier also, this I can be taken outside. So, this becomes I into f inverse of 1 by s square plus 1 by 1 plus s square whole square. That is equal to f inverse of 1 by 1 plus s square into 1 by 1 plus s square. Now, let us apply convolution theorem here. F inverse of f of x into f of g of x is equal to f of x star g of x. That is f inverse of 1 by 1 plus s square into 1 by 1 plus s square is equal to f inverse of 1 by 1 plus s square star f inverse of 1 by 1 plus g square. This we obtain using convolution theorem. So that is equal. Now let us multiply these two terms with 2. 2 here, 2 here. So we get 4 in the denominator here. So this is equal to I by 4 into f inverse of 2 by 1 plus s square star f inverse of 2 by 1 plus s square. And we know that f inverse of 2 by 1 plus s square is e power minus mod x, because f of e power minus mod x is equal to 2 by 1 plus s square. Therefore, f inverse of 2 by 1 plus s square is e power minus mod x. So this is equal to I by 4 times e power minus mod x star e power minus mod x. And star is convolution product there. You know that it is given by f of x star g of x is integral 0 to infinity, minus infinity to infinity f of u into g of x minus u du. So if we apply the definition of convolution product for these two functions, we get integral minus infinity to infinity e power minus mod u. We need f of u here. So in place of f of u, we get e power minus mod u into g of x minus u. So this is e power minus of x minus u du. So now we have to evaluate this integral. For that, we split integral minus infinity to infinity as minus infinity to 0 plus 0 to infinity. Between minus infinity and 0, mod u is equal to minus u by the definition of modulus function. So minus of minus becomes e plus. So this is e power u into e power minus mod x minus u du plus. In the interval 0 to infinity, mod u is equal to u. Therefore, this becomes e power minus u into e power minus mod x minus u du. Now, let us further split this integral minus infinity to 0 as minus infinity to x plus x to 0. And the integral 0 to infinity as 0 to x plus x to infinity. Because we have mod x minus u here, in each and every term we have mod x minus u. To write the definition of mod x minus u, we are splitting the integral. Now, if we look here, in the interval minus infinity to x, that is u lies in the interval minus infinity to x, that is minus infinity less than u less than x. Excuse me. In the first integral, we have minus infinity is less than u less than x. Is less than x. Therefore, x minus u is positive here. X minus u is positive in this case. Therefore, in the first integral, we get integral minus infinity to x e power u into e power minus of x minus u du. Plus, now come to second integral. U lies in the interval x to 0. Therefore, x minus u is negative, and hence e power mod x minus u becomes minus of x minus u, that is e power x minus u. Similarly, in the third interval 0 to x, that is u lies between 0 and x, therefore x minus u is positive, and hence e power minus mod x minus u is e power minus of x minus u. Similarly, in the last integral x to infinity, that is u lies in the interval x to infinity in the last integral, therefore x minus u is negative, and hence e power minus mod x minus u is equal to e power x minus u. So after writing the values of mod x minus u, we get this integral I by 4 times integral minus infinity to infinity e power u into e power minus of x minus u du plus integral x to 0 e power u into e power x minus u du plus integral 0 to x e power minus u into e power minus of x minus u du plus integral x to infinity e power minus u into e power x minus u du. And if we simplify, e power u into e power minus x into x minus u gives e power minus x into e power 2u. And here e power u, e power minus u gives 1. So we have e power x here. See here also e power minus u into e power u becomes 1. We remain with e power minus x. And in the last integral we have e power minus 2u into e power x. Because the integration is with respect to u here, we take the x terms outside. So this is e power minus x into integral minus infinity to x e power 2u du, e power x into integral x to 0 1 du, e power minus x into integral 0 to x 1 du, e power x into integral x to infinity e power minus 2u du. We know that integral of e power ax is equals to e power ax by a. Therefore, integral of e power 2u is e power 2u by 2 here. Integral of 1 is u within the limits x to 0, and here integral of 1 is u in the limit 0 to x. Integral of e power minus 2u is e power minus 2u by minus 2. Now if we substitute the limits, in the first term e power 2x minus e power minus infinity becomes 0 here by 2 plus. In the second term e power x into 0 minus x plus e power minus x into x minus 0 minus e power x into e power minus infinity is 0 minus e power minus 2x by 2. So after simplification, we get I by 4 times e power x by 2 minus x into e power x plus x into e power minus x plus e power minus x by 2. Now grouping first and last terms, we get e power x plus e power minus x by 2 minus, taking out x common in second and third terms, we get e power x minus e power minus x. And we know that e power x plus e power minus x is 2 cos x. Therefore, this is 2 cos x by 2. Hence, this is cos x. And e power x minus e power minus x is 2i sin x. Therefore, finally, we obtain 1 by 4 times 2x into I becomes I square, that is minus 1. Minus minus becomes plus. Therefore, this is 2x sin x plus I into cos x. Therefore, this is inverse Fourier sine transform of I by 1 plus s square whole square. Thank you. Hope you understood these problems. Thank you.